Okay, let's unpack this. Today, we're diving into the fascinating world of organic molecules.
Yeah, it's a huge topic.
There really is. We're going to explore their incredible structures, their real-world uses, and, the fundamental principles behind how we understand and even build them. Our mission, to pull insights directly from a core resource, organic chemistry, I for Dummies, seconded, and really extract the most important nuggets of knowledge.
Sort of a shortcut.
Exactly. Think of it as a shortcut to being truly well-informed in organic chemistry. We'll have some surprising facts, clear explanations, and hopefully just enough humor to keep you hooked.
Sounds good.
All right, here's where it gets really interesting. We're starting our deep dive with a look at 10 organic molecules that are just, well, plain fascinating, either for their structure or their impact.
Right. It's a great way to see the diversity.
It really showcases the immense diversity of organic chemistry.
And what's truly remarkable here, I think, is how these seemingly disparate structures, they highlight core principles and often, surprising real-world applications.
Okay, so where do we start?
Let's start with octanitrocubane. This is an organic explosive. Now, to understand it, you need to know that organic explosive, they basically combine a fuel like the hydrocarbons in TNT's benzene ring
You okay?
and an oxidizer like nitro groups, all within the same molecule. Then, an initiating event, maybe heat, shock, or light, triggers this uncontrollable oxidation reaction. It generates pressurized gases, immense heat.
A shockwave, right.
Exactly, a powerful shockwave.
So what makes octanitrocubane different, like so potent?
Well, it's unique because it holds a great deal of energy in its highly strained rings. Imagine stretching a spring to its absolute limit.
Right.
That stored tension is sort of like the energy in these bombs. This strain means that when it explodes, it releases more heat compared to less strained compounds,
Oh, okay.
which gives it the highest detonation velocity of any known explosive. The deeper insight here is that even subtle things like molecular strain can unleash tremendous energy. It's a principle chemists use for, well, all sorts of things.
But there's a catch.
Oh, yeah. The drawback, its synthesis is incredibly difficult.
Right.
And expensive, which is why you don't really hear about it much.
Fascinating.
Okay.
Okay, from raw power, let's shift to something that feels more like chemistry as art. Fenestrine. What's the story there?
Fenestrine is visually stunning, really. It consists of 4 cyclobutane rings all joined together, makes for a highly strained but quite elegant structure.
And the name.
It's called fenestrine, from the Latin word fenestra, meaning window, because its shape literally resembles an old-fashioned window pane.
Cool. And speaking of structures that grab your attention, we absolutely have to talk about carbon nanotubes.
Why, yes. Carbon nanotubes. These are a recently discovered allotrope of carbon.
Allotrope meaning.
Just a different structural form of the same element. So think of them as individual sheets of graphene, which are basically flat planes of fused benzene rings that have been rolled up to form tiny cylinders.
And they're strong.
Their properties are truly extraordinary. They are the strongest materials known, many times stronger than steel. Plus, they have incredibly high thermal and electrical conductivities.
Wow. So what's the holdup? Why aren't they everywhere?
Well, the current challenge is really scaling up production. We need new methods to make them cheaper and on a larger scale for widespread use.
Makes sense. Okay, so from super strong materials, we shift to something that sounds like a molecular magic trick. Boulvalene. You mentioned it's a molecular shapeshifter. How does that work?
That's right. Boulvalene is captivating because at room temperature, the molecule just interconverts rapidly between numerous identical forms. It's constantly rearranging its atoms.
Seriously.
Yeah, and the astonishing consequence is that all 10 carbons become equivalent in solution. So if you were to look at its 1H NMR spectrum, that's like a molecular fingerprint for hydrogen atoms,
Right.
you'd see just a single peak at room temperature.
Just one for 10 carbons.
Just one. But here's the cool part. If you lower the temperature, the shape shifting slows right down. And then you can observe multiple proton absorptions, the distinct signals you'd normally expect.
That's incredible. And the name.
It's named after William During. His nickname was Bull. A fun little chemist's inside joke.
Love it. Okay, that's wild. And
Yeah.
now for some chemical drama. The Norbornal cation. You said it was at the center of a huge controversy.
Oh, absolutely. For decades, it sparked this fierce debate. On one side, you had Nobel laureate two equivalent carbocation forms.
Carbocation being a positively charged carbon.
Exactly, just by shifting atoms around. But then Saul Winstein proposed a single, more stable, non-classical structure, kind of a hybrid of two resonance structures, ways to show how electrons are spread out.
So, like two different pictures of what it looked like.
Sort of. The debate was intense. Both sides were pretty dug in. However, after a lot of experimental and theoretical work, most scientists now agree the structure is indeed that bizarre-looking non-classical form. It really shows how science figures things out, even when it's messy.
A real scientific saga.
Okay.
From controversy to a compound that literally adds spice to our lives. Capsaicin. What's the chemical secret behind chili heat?
Right, capsaicin. It's the main compound giving hot peppers their heat. The Scoville unit, that measure of pepper heat, it directly scales with the amount of capsaicin.
Makes sense.
But what's really interesting about its structure is it has this long, greasy, hydrophobic tail.
Hydrophobic.
Water-fearing.
Exactly. So it doesn't dissolve well in water. And that is why milk, which has nonpolar fats, is recommended to cool the burn. Those fats can solubilize the capsaicin much better than water can. They basically wash it away from your pain receptors.
Ah, so that explains why water just seems to spread the pain around.
Pretty much. And the burning sensation itself. Capsaicin actually activates the same pain signaling pathways as real heat burns. Ouch. Okay, next up, a compound that literally changed the fashion world. Indigo.
Yeah, indigo, the classic blue compound. Initially, it was isolated from indigo plants.
It was a big deal back then.
Hugely desirable. Blue dyes were exceptionally rare when it was discovered. Of course, while it started from plants, today, indigo is made synthetically, by the metric ton, actually, primarily for dyeing blue jeans.
Wow. So it went from rare natural product to this massive industrial chemical.
Exactly. Shows the power of organic synthesis.
And now for what you call the beast of an organic molecule.
Yep.
Adotoxin.
Oh, this one is. It's truly monstrous, both in size and impact. It contains 32 fused ring systems and an astounding 98 chiral centers.
98. Remind me what a chiral center is.
It's a carbon atom with 4 different groups attached. It gives the molecule a kind of handedness, like your left and right hands.
Got it. So very complex and dangerous.
Extremely. It was isolated from a tropical fish, and it is the most toxic small organic molecule known. Its LD50 in mice is 50 nanograms per kilogram. I mean, to put that in perspective, a single gram could potentially kill hundreds of thousands of people.
That's terrifying.
It really is. It's complexity.
Well, it makes you grateful for the problems you get in a typical organic chemistry class. And it highlights the immense challenge in, say, solving its structure using NMR spectroscopy or trying to propose a multi-step synthesis to actually make it.
People are actually trying to synthesize it.
Oh, yes. Current synthesis efforts are underway. The chemists working on it are tackling a monumental task. It really pushes the boundaries of our ability to build molecules.
Both terrifying and awe-inspiring. Okay, speaking of complex structures and building, let's look at molecular cages. What are these?
Molecular cages are fascinating. They're organic structures that contain cavities specifically designed to trap other atoms or molecules inside.
Like tiny, custom-built molecular prisons. That's a good way to think about it. For example, crown ether cages. They look like crowns, and they can trap metal ions like potassium right in their central cavity.
Okay.
Then you have calixarenes. They look sort of like shuttlecocks and can hold small organic molecules. And then there are cyclodextrins.
I think I've heard of those.
Probably. They're rings of connected glucose molecules famously found in products like Febreze.
Febreze, how do they work there?
They encapsulate those volatile, foul odor compounds in their sort of donut hole-like cavity. Traps them so you can't smell them.
That's clever.
Yeah.
So what's the future potential for these cages beyond air fresheners?
Well, a lot of scientists are testing related molecular cages as drug delivery vectors.
Meaning?
Imagine being able to carry toxic drugs, like chemotherapy molecules, directly to a tumor site while minimizing side effects on healthy cells. That's the kind of promise these structures hold.
That would be huge. Okay, and for our final cool molecule, we have fusidyl. This one sounds almost whimsical.
It does sound a bit whimsical. Fusidyl is the reduced form of fucose. Fucose is a naturally occurring deoxysugar.
Deoxysugar, meaning it's missing an oxygen.
Missing an OH group, yeah. An oxygen-hydrogen group. Fusidyl itself is an alditol. It's produced by reducing the aldehyde part of an aldose sugar, like fucose, using a reagent called sodium borohydride.
And where do you find it?
It's found naturally in seaweed. And yes, there's this playful speculation that A dose of fusidal might change an attitude of anxiety and stress from organic chemistry to a more Zen-like outlook.
Huh? Maybe we all need some after this deep dive.
Perhaps. It's a fun thought.
These molecules are incredible. They really highlight the diversity and just the sheer ingenuity of organic chemistry. But, how do chemists even begin to create such wonders?
Yeah.
Or understand how they work? That leads us perfectly to the art of multi-step synthesis.
Right, and this raises a really important question. Why do chemists put so much effort into multi-step synthesis? And maybe more practically for listeners, how can you effectively tackle these problems, which can often be quite challenging?
So why do chemists do it? Isn't it easier to just find stuff in nature?
Well, historically, many drugs did come from natural sources. Think opium, aspirin from willow bark, penicillin from mold.
Sure.
But relying on natural extraction has big problems. The sources can be rare, sometimes endangered. It's often really hard to separate the active compound you want from all the other stuff in there.
Impurities and things.
Exactly. And natural sources rarely produce high quantities. You might start with thousands of pounds of plant material and end up with just a few milligrams of the drug. Not very efficient.
So multi-step synthesis is the answer to that problem. It allows chemists to...
Precisely. To make compounds pretty much from scratch. Chemists take commercially available, often simple, starting materials and build the desired molecule using known reactions and techniques.
And that's how most modern drugs are made.
Many of them, yes. It's planned meticulously, usually on paper first, to find the shortest, cheapest routes. Those are big priorities in the pharmaceutical industry, obviously.
But it's not just about drugs, right?
Oh, definitely not. Synthesis gives chemists, well, sort of free rein to create almost any compound imaginable. This leads to developing new reactions, testing known methods, and sometimes it's even a way for chemists to kind of flaunt their synthesizing prowess.
Like building a really complex Lego set.
Sort of. It's the ultimate chemical puzzle. And interestingly, even failure is valuable.
How so? So even when a planned reaction doesn't work, it can still lead to breakthroughs.
Absolutely. When planned reactions fail in the lab, it often leads to discovering completely new reactions or gaining deeper insights into how molecules behave.
Can you give an example?
A great one is the synthesis of vitamin B12. It was known pretty much from the start that synthesizing it on a commercial scale would be impractical, just too expensive. But the effort was incredibly valuable to organic chemists. It led to the discovery of many new synthetic techniques and, importantly, a major theoretical breakthrough in understanding a class of reactions called pericyclic reactions, like the famous Diels-Alder reaction.
So even though it wasn't practical for making B12 pills, it pushed the whole field forward.
Immensely. It added a huge amount of knowledge. Science, for science's sake, sometimes pays off big time down the road.
That's a great point. Okay, now, for tackling these synthesis problems yourself, you mentioned the 5 commandments for multi-step synthesis problems. Let's break those down.
Right. First, let's just define the problem type. In these synthesis problems, you're given a starting material and a desired product. Your task is to figure out a route, a sequence of reactions to get from start to finish.
What do you need to show?
You need to provide the specific reagents for each step and show the intermediate compounds formed along the way. Importantly, you don't need to show the mechanisms, the arrow pushing for the individual reactions, just the reagents and the molecules.
Got it. No arrows needed here. So what's the first commandment?
Commandment 1, thou shalt learn thy reactions. This is absolutely fundamental.
Yeah.
You must memorize the reagents and the transformations they perform. What does this reagent do to this type of molecule?
No way around the memorization, huh?
Not really. Organic chemistry is cumulative. You have to constantly review all the reactions you've learned. Flashcards can be really helpful here. It's definitely not something you can cram effectively the night before.
Okay, learn the reactions. What's number 2?
Commandment 2. Thou shalt compare carbon skeletons. This should be the very first thing you do. Look at the carbon backbone of your starting material and compare it to the backbone of your product.
What are you looking for?
Did you add carbons, lose carbons, rearrange carbons, and identify where those changes happened? This simple step helps organize your thoughts, even for really tough problems.
Okay, compare the skeletons. Now, number 3 sounds intriguing. Working backward.
Yes, Commandment 3, thou shalt work backward, retrosynthesis. This is a powerful technique. It's like solving a maze by starting at the exit and working your way back to the entrance.
How does that work chemically?
You start by looking at your final product. Then you brainstorm all the reactions you know that could possibly form that specific product. Temporarily ignore your starting material. Then, for each potential reaction you thought of, you ask, What reactant would I need to make that reaction happen? What's the immediate precursor?
Right.
Then you compare those potential precursors to your actual starting material. Which one looks most plausible or easiest to get to from the start? That becomes your target for the previous step.
And you just repeat that process.
Exactly. You repeat it for that precursor, working backwards step by step until you eventually arrive back at your original starting material. As you get closer to the start, you refer back to it more often.
What if a path doesn't work out?
Just go back and try another one of the potential reactions you brainstormed. Don't get discouraged. Intuition for this definitely comes with practice.
Okay, work backward. So once you think you have a potential path, you need to check your work. Is that the next one?
Okay, got it. Commandment 4. Thou shalt check thine answer. Once you have proposed synthesis on paper, review each step very carefully.
What are you checking for?
Critically, ensure that all the reagents you propose for a given step are actually compatible with all the functional groups present in the molecule at that specific stage.
Functional groups being those specific arrangements of atoms, like alcohols or ketones.
Exactly. Some reagents react with multiple functional groups. You need to make sure your chosen reagent only does what you want it to do in that step and doesn't mess up another part of the molecule unintentionally. Professors often include tricks related to this, so double-check every detail.
Good tip. Okay. And finally, the greatest commandment of all.
Commandment 5. Thou shalt work many problems. This really is the most important one. There's no magic formula, no substitute for extensive practice.
That's got to do the reps.
You really do. Start with easier synthesis problems to build confidence and understanding. Then gradually move to more challenging ones. And this is key use solutions manuals only after you have made a genuine, honest attempt to solve the problem on your own.
Why is that so important?
Because looking at a solution and thinking, yeah, okay, I see how they did that, is completely different from the learning that happens when you struggle through it yourself and figure it out, or even just figure out where you got stuck. That's where the real understanding develops.
Makes total sense. Okay, so we've explored the art of building molecules with synthesis. Let's now turn our attention to the how behind the build, reaction mechanisms. If synthesis is about creating, mechanisms are about understanding the precise dance of electrons that makes it all happen.
You're absolutely right. Knowing a reaction's mechanism is vital. It's the detailed step-by-step process that uses those curved arrows to show how electrons move during a reaction.
Bond breaking and bond making.
Exactly. A complete mechanism shows all the bond-making and bond-breaking steps and any intermediate species that are formed along the way. And this knowledge, it's crucial for optimizing reaction conditions, predicting if a reaction will even work, or maybe figuring out why it didn't work.
So how do you approach learning mechanisms? Are they all the same?
Well, from a practical standpoint, especially when you're learning, you'll encounter kind of two main types of mechanisms you need to master.
Okay, what are those?
First, there are mechanisms to simply learn. Some mechanisms are just, well, really complex, or they involve unusual intermediates that you wouldn't easily figure out on your own. You basically just have to commit them to memory.
Like which ones?
A classic example is the bromination reaction of alkenes. It involves this weird three-membered bromonium ion intermediate. It's not something you'd likely deduce just from general principles.
Okay, so some you just memorize. What's the other type?
Then there are mechanisms to work out on your own, and for these, memorization is pretty much useless. Professors often expect you to be able to deduce mechanisms for reactions you've never seen before.
How can you do that?
By applying the general principles of arrow, pushing how electrons tend to move. This is where extensive practice becomes absolutely critical. You learn the patterns.
Okay. So for those work out on your own mechanisms, what are some practical do's and don'ts for drawing them correctly, getting the arrows right?
Yeah, there are quite a few critical ones. First big one, don't confuse mechanism problems with multi-step synthesis problems. Remember, mechanism problems provide all the reagents needed. You should not be supplying additional ones like you do in synthesis.
Okay, use only what's given.
Right. Which leads to the next point. Duo use all the reagents given. Every single reagent provided in a mechanism problem usually has a specific role to play. If you haven't used something, you might have missed a step.
And what about recognizing what not to include? Things that are just there.
Good question. Don't confuse solvents and base scavengers with active reagents. You need to recognize common solvents, THF, DMF, DMSO, chloroform, dichloromethane, stuff like that. They generally don't participate directly in the electron pushing. Unless the solvent is something like an alcohol or water, which can be involved in proton transfers moving an H+ around. Also, things like pyridine or triethylamine are often just base scavengers. They're to neutralize acid that might be formed, not usually part of the core mechanism arrows.
Okay, be selective about what you draw arrows from.
Exactly. And related to drawing, do you get in the habit of drawing out all the atoms at the reaction centers? Use full Lewis structures showing all the valence electrons, especially for the parts of the molecule that are changing.
Why is that so important?
It makes it so much easier to track atoms, bonds, and especially charges. It helps prevent common mistakes like losing atoms, misplacing charges, or drawing bonds incorrectly.
Makes sense. Be explicit
Yeah,
and take it slow.
definitely. Don't try to do two things at once in a single mechanism step. Take each transformation one step at a time. Even if a single conceptual step involves multiple arrow-pushing events, draw them clearly.
Like if you protonate something and then something leaves.
Right. Like protonating an alcohol and then kicking off water to form a carbocation.
Yeah.
Show those as two distinct steps with their own sets of arrows. Don't combine them.
Okay. What about intermediates?
DO, draw out all resonance structures for intermediates. It's really good practice, even if it's not explicitly required for points, especially for reactive intermediates like carbocations or the intermediates in electrophilic aromatic substitution. It helps you understand their stability and reactivity.
And always keeping the final product in mind, like in synthesis.
Always. Do look where you're going. Just like planning a trip, know your destination. Understand what bonds need to break and what bonds need to form to get from the starting material to the product. This helps make sure each arrow you draw is actually leading you in the correct direction.
What about side reactions? Should you worry about those?
Generally, don't overanalyze why you wouldn't get a different product than the one indicated. Your main task in a mechanism problem is to explain how the given product is formed. Draw that mechanism first. You can explore the why not something else questions later if you have time.
Focus on the goal. Any other common pitfalls? Things that make professors cringe?
Oh, yeah. Do we ignore spectator ions? When you see reagents like potassium hydroxide, KOH, or sodium methoxide, no way. Mentally cross off the K+ or Na+ to air. Rewrite the reagent just showing the active part, like OH or MAMIO.
Why ignore them?
It prevents the temptation to draw arrows involving these spectator ions. They're just counterions. They don't participate in the electron-pushing part of the reaction.
Got it. Just the reactive bits.
And maybe the most crucial check. Do you ask yourself if all your proposed steps and intermediates are reasonable? Are they chemically sound?
What makes something reasonable or unreasonable?
There are key rules. Nucleophiles, remember, electron-rich things. Nucleus lovers attack electrophiles, electron-poor things, electron lovers, never the other way around.
Yeah.
Also, think about the reaction conditions. In acidic conditions, you generally avoid forming strongly basic, negatively charged intermediates, unless it's the conjugate base of the acid you used.
Yeah.
In basic conditions, you avoid forming strongly acidic, positively charged intermediates.
Acid stays acid-like, base stays base-like.
Pretty much. And fundamentally, make sure you never, ever draw a pentavalent carbon, a carbon with 5 bonds. Always obey the valence rules for all atoms. And finally, do all the charges balance at each step. The net charge should be conserved throughout the mechanism.
That's a lot to keep in mind. But it sounds like a good checklist.
It is. And finally, DO be able to work the different types of mechanisms. With practice, you'll start to recognize patterns and similarities.
So what are the main categories of mechanisms you'll encounter as you practice?
Well, you'll see thermal mechanisms. These reactions just proceed with heat, no other reagents needed. The Diels-Alder reaction is a prime example.
Okay, heat only.
Then, probably the most common type you'll see is nucleophile electrophile mechanisms. These involve a nucleophile attacking an electrophile. It covers a huge range of reactions.
Right, the electron-rich attacks the electron-poor.
Exactly. Then you have acid-base mechanisms. You can usually spot these by the presence of a strong acid, like HCl or H2SO4, or a strong base, like NaNH2, as a reagent. Remember the rules. Under acidic conditions, the first step is usually protonation, adding H+, and avoid strong bases. Under basic conditions, the first step is usually deprotonation, removing H+, and avoid strong acids.
Okay, acid-base driven.
Related to acidic conditions are carbocation mechanisms. These generally happen under acidic conditions. A key thing here is to always be alert for potential carbocation rearrangements, things like alkyl shifts or hydrogen shifts, where the carbocation rearranges itself to form a more stable one before the next step happens.
They can shift around.
They can be.
They can be.
Then there are anion mechanisms. You see these mostly in carbonyl reactions involving ketones, aldehydes, esters, etc., and they usually occur under basic conditions. You'll likely see more of these in the second semester of organic chemistry.
Okay, anion means negative charge, often under basic conditions.
Correct. And finally, there are free radical mechanisms. These are less common in intro-organic, but you can identify them by reagents like light, often written as high, or peroxides, ROR.
And drawing those is different.
Yes. When drawing these, you use half-headed arrows, like a fishhook, to show the movement of just one electron at a time, since radicals involve single, unpaired electrons. It's also standard practice to detail the distinct initiation, propagation, and termination steps for radical reactions.
Wow. So understanding these categories helps you know what patterns to look for.
Precisely. It helps organize your thinking when you're faced with a new mechanism problem.
Wow, what a journey. I mean, from the explosive power of octanitrocubane and that amazing shape-shifting boulevine,
Cool stuff.
all the way to demystifying the art of multi-step synthesis and understanding the really intricate electron movements in reaction mechanisms. We've truly taken a shortcut to being well-informed today.
Indeed. Hopefully this deep dive has illuminated not just the what, but also the why and the how behind organic chemistry's, well, incredible beauty and its practical utility.
Definitely.
And remember, that critical thinking, whether you're working backward in synthesis or meticulously checking each step of a mechanism, that's truly essential for getting a handle on this field.
It really shows that whether you're, building a life-saving drug or just understanding why milk soothes a chili burn, or even contemplating that Zen-like outlook on your studies from Fusital, organic chemistry is just all around us, with incredible stories and insights just waiting to be discovered.
And that actually raises an important question, maybe something for you to think about. What other everyday substances might hold hidden chemical complexities that, once you unpack them, could truly surprise you?
Something to mull over as you go about your day.
Yeah.
Thank you so much for joining us for this deep dive into the fascinating world of organic chemistry.
My pleasure.
We really hope you gained some valuable knowledge and maybe had a few aha moments along the way.